So to those who are already here, welcome to Classical Mechanics 1. I hope I am audible. Can
yes,
somebody? Okay.
Yes,
okay, great. Yeah. Yeah, so it would be good if people are come about certainly by the starting time of 11:50. You are welcome 5 minutes in advance as well.
Sir, our previous lecture just ended like 2 minutes ago, so people are still joining.
Okay. All right, so that ended at 11:45, is it? Okay.
Yes, sir. Sir extended a little bit, so we left at 11:49 or something. So we're still joining.
Wow. Okay. Well, then you are excused. Okay. Perhaps you need a break then. Fine. And how many were you in your previous lecture?
Sir, about 65, 70.
Okay. All right. Yeah. So, and what was the previous lecture?
Analysis 1 by Rajiv Karandega, sir.
Okay. Analysis 1. Fine. Yeah. So we have 35 people right now. Yeah. Today we are going to just get started, and we're not really going to get into the heart of classical mechanics. I plan to do some a little bit of mathematical background, and also to bring us all on a common page. But I'm still waiting for people to join.
So at the end of the class, people were still asking some doubts, so that might be the reason why it's slightly difficult.
Okay. So we will need to make some allowance for that, or ensure that the previous class ends on time. Fine. Yeah, thanks for letting me know. So I presume many of you have learned some amount of classical mechanics or mechanics in school or during other courses. So there will be some things here which are very familiar. There will be things that sound familiar, but when you look at them in greater depth are not so familiar. And there will be things that are quite new, I hope. Please bear that in mind while we go through things. Okay, we have 58 people and we are now 4-5 minutes into the class. Yeah. 65 to 70 is what I have to. Yes, please do have a copy and a pen. It's a good idea. I had a teacher once, a complex analysis teacher, David Prill. He told me that you learn through your fingers by writing also. You learn through your ears and eyes also by reading, but also by writing. So please do have a paper and pen. It's not like you have to write everything down, but there's no harm in writing some equations or even a question that you have, something that you had a doubt about to keep there perhaps. Yeah, I mean, it's a skill to know what and how much to write down. And by attending a lecture, you develop that skill. Yeah, 61. So while we still wait for others Let me continue with these generalities. Yeah, so I think you've all received my email, and there will be stuff posted both on Moodle as well as on the course website, whose link I have sent you. The course is largely defined by the lectures themselves, and there may be notes that I make available as well. So those would be what defines the course. There are books that one can consult as well, which I will suggest. One of them is by Klepner and Kolenkov on mechanics. It is available in Indian edition, Cambridge University Press, second edition, at a discounted rate. An introduction to mechanics. So this is a nice book, and there are many other books as well. I will mention others as we go along. There's one by David Morin. There's books by in the Berkeley series by Kittel and about 4 or 5 other authors. There is the Feynman lectures in physics. So there are several sources, and but in addition to all of that, the main thing is the lecture itself, and the discussions we have. Do we need to have all the books you mentioned, sir, or just one of them? You don't need to have any of them. If you want to get just one of them, you can get perhaps the one by Klepler and Kolenkov. You don't need to have all of them, no. But you do need to attend the lectures and be involved and work out the problems that are assigned. That is quite important. If there is specific reading that I assign, then I will tell you where to look those things up. The books I have mentioned, I believe, are all available in Indian edition, relatively reasonably priced, if you would like to purchase any of them. Any other questions on general matters at this stage?
Sir, who are the TAs for the lecture?
Yeah, so today we have 2 of our graduate students helping us. One is Ankit, the other who is here as a co-host, as well as Pritish Sinha, joining us from Hazaribagh. Ankit is in Chennai. And there are additional TAs who are not present here, who will be involved with other lectures as well as perhaps tutorials, grading, and so on. I will introduce the other tutors. One is Advait Fadnis, and there is Vishnu Kadiri and Shubhendu Prasad Mandal. So we will be assisted by all of these people. Any other questions at this stage? We have 65 persons, students with us. That includes, I don't know, that includes me and the 2 TAs. So we really have only 62 students. Fine. Okay, but I think, these different books have different viewpoints. Some may be somewhat more phenomena oriented. Some may be more theoretically oriented. So some may give more background, some may give more problems. So it's but somebody joined and wanted me to repeat the reference books. Now tell me, if you join late, can you still see the text box, the chat box? Or is that invisible?
Yes, sir. If we join late, we can't see the previous messages, but we
Ah, okay. So let me repeat some of that. Yeah, one good book is the one by Klepner and Kolenkov. Yeah, so I will, if you want to buy one, this is a nice one. On an introduction to mechanics, Cambridge University Press, 2nd edition. It's available in Indian edition, I think just short of 1,000 rupees. I also mentioned the book by David Morin. I also mentioned a book in the Berkeley Physics series by Kittel and other authors. Yeah, so the one main message is to try to be here on time so that we don't have to repeat things. Yeah, and then there are the Feynman lectures in physics, the first volume, which is a very a deep presentation of physics. Yeah, so and the list goes on. I think there's one by there's one by Newton. In fact, there are several Newtons, but there is one by Isaac Newton. It's called the Principia, Principles of Natural Philosophy. At some point, you may want to look up something about that. Yeah, anyway, so jokes apart, the primary book for this course is the lecture. I will also try to provide some lecture notes, and they will define the course. It may be supplemented by these other books. You are, if you would like to buy one, I suggested the one by Klepner and Kolenkov. Yeah, the others are also excellent ones. I will make a list of books and put them on the course website. Okay, any other questions at this stage? All right, in that case, let us get started with the lecture proper. We have around 63 participants. Okay, so I will share my screen, where I hope you will be able to see things. Okay, so please do stop me if you cannot hear me clearly or cannot see the shared screen properly, because I want to ensure that such basic problems are dealt with, which will allow us to focus on other things. So the initial today's lecture will primarily be on a primer on vectors, yeah, and some of their properties. A lot of this may be familiar to some of you, some of it may not. The viewpoint also may be a bit different than what you're familiar with. So I suggest that if things seem very familiar to you, please still stay tuned in. In many ways, the purpose of attending a lecture is to know how things are presented and how you think about things and how do you visualize things, as much as it is to learn an equation. Viewpoints are very important, and also emphasis. I mean, it's important to know what's important and what's less important. Yeah, because a book has 500 pages, so we make a selection as to what is important. Yeah, and a little bit of patience is also called for. There may be parts that you are familiar with, and all of a sudden there may be things that you are unfamiliar with. So stay tuned in. We will have assignments quite regularly, which are to be turned in to various TAs. And so please stay up to date with such things. Okay, so are you able to see my shared screen?
Yes, sir.
Okay, great. So let us talk a little bit about vectors. Vectors provide a convenient way of writing the equations of physics in compact form. Yeah, I mean, this is a very pedestrian way to put it, but it is still true. For instance, yeah, I think people are still joining. So it may be possible for me to provide a recording of this lecture. I do not guarantee that. I make no secret of the fact that attendance is required and being present on time is also required. Of course, I do understand if the previous lecture ended a little bit late, we will make allowance for that. But do not expect lectures to be available online or elsewhere. They have to be attended, and they are not optional. Everything in the lecture is a potential question for examination. Yeah, so as I was saying, vectors provide a convenient way of writing the equations of physics, and not just physics, also various areas of mathematics in a compact form. For instance, Newton's second law, which we will talk about in much more detail, which in Newton's time was written as 3 different equations. The x component of the force is equal to mass times the x component of acceleration. The y component of the force is equal to the mass times the y component of acceleration, and the z component of the force is mass times z component of acceleration. So it took me a while to just read out that equation. I did it on purpose. It's because this set of 3 equations becomes a single equation. A vector f, which I've written in boldface, is equal to mass times acceleration, which is again a vector written in boldface. M is the mass of the particle, and this is called Newton's second law. Now, okay, just to give you an anecdote, it really took a long time for vector notation to become standard or even to be invented. In Newton's time, it simply was not there. Even in Maxwell's time, I mean, Newton is from the late 1600s. 1687 is when his great work was published. Even in Maxwell's times, which was in the 1860s, Maxwell did not write his equations of electromagnetism in vector form. He wrote them in component form. And very interestingly, he had to invent lots and lots of notation just to accommodate all the equations. So the magnetic field has 3 components, the electric field has 3 components, so he needed different letters of the alphabet for each of these. For instance, the magnetic field is called H, yeah, H for house. Now you may wonder why it's called H, is a weird letter in the middle of the alphabet. The reason is something more rather mundane. He started with E, F, and G for the electric field. So the first component of the electric field was E, and then F for the second component, and then G for the third. And then when he wanted to go to the magnetic field, he had to take another letter, and therefore it was H. So yeah, and if you actually look at Maxwell's work, it is rather, I mean, it's the writing itself is very elaborate, and it was in the time of others, notably Gibbs, who was one of the first American mathematical physicists who really made vector notation more commonly used. Yeah, so notation is extremely important in science. Let me also tell you one more anecdote. Some time ago, Professor Srinivasa Varadhan, who is a Nobel Prize winner, was here at CMI lecturing. And in the middle of his lecture, he wondered how it was that people like Aryabhatta could do mathematics or physics or astronomy without apparently having notation. I mean, they presented their work in poems. I mean, exquisitely crafted poems, very pithy statements and sutras and bhashyas and so on. But he was really surprised how they were able to think without notation. But perhaps they had notation, but they have not just not revealed it to us. Yeah, so notational superiority is actually scientific superiority. There are groups of people who simply don't have the right notation and are not able to make progress. or it slows down progress. Okay, so let's also go ahead with some other uses of vectors. So vectors also make it easier to understand structural features of equations and phenomena. So for example, the behavior of things under rotations, yeah, it's very hard to understand it if you write 5 equations when you can compress it in one and see how it changes. How symmetries like rotations or translations or reflections and such things are implemented. It's easier to see them in vector notation. And also transformation laws. I mean, how does Galileo's idea of transformation from one reference frame to another one that is moving uniformly, how do you think about such things? Vectors make it very convenient to formulate such questions and answer them. So the message is that vectors make it easier to understand structural features and reveal hidden features of equations which you would not otherwise notice. Yeah, so I mean, for instance, in our modern parts of physics like supersymmetry, there is a plethora of notation. So I mean, this is not a discussion about supersymmetry, but it's almost as if this notation is so complicated that it almost feels as though we are waiting for some better notation to really understand what things at a deeper level. In some areas at least. So we are just seeing this from a couple of centuries ago, this the revolution that vectors brought about. So vectors also allow us to bring to bear tools from linear algebra, which we will talk about, as well as geometry. Yeah, so that's very helpful. So let me begin by giving a somewhat simple definition of, okay, let me not scroll too fast, of what I mean by a vector in three-dimensional Euclidean space. So when I say three-dimensional Euclidean space, I basically mean the space in this room, the space around us, and extended indefinitely. I mean, I forget about the walls and windows and so on, up, down, left, right, yeah. Three-dimensional Euclidean space. So this is named after Euclid. Now, a vector in three-dimensional Euclidean space is a directed line segment like the one drawn in this picture. Yeah, a directed line segment. So it's a line segment. It starts at an origin. So here's my origin, and it's a line, and it ends somewhere, and it has a direction as well, which is indicated by this arrow. We call it a boldface V. Yeah. Sometimes we use a different notation, which is a vector with an arrow on it. So I will sometimes denote it this way, especially when writing by hand. But if I'm typing, I use boldface notation. Now a vector has 2 basic ingredients. One is its magnitude, which is denoted by this absolute value sign, or sometimes called the modulus or length of the vector. And that length of the vector itself is denoted with a V without the boldface. Yeah. Yeah. And in addition, so the magnitude of boldface V is ordinary V. A vector also has a direction. So this one points roughly towards, let us say, Tripura or something like that. And the length is what is indicated. Okay, so I mean, we will redefine what we mean by a vector or further elaborate on this later on, but this is not a bad definition, in fact. Though you may have seen other definitions. There is some deep value to this, in the sense that it is defined independent of any choice of axes. It is defined independent of any coordinate system. It is defined in terms of physical quantities. Like I said, an origin, okay, it's me, I'm the origin. So that's a physical quantity, and it's pointing towards Tripura, right? That's another physical quantity. So notice that the way we have defined this is in a very concrete way. It doesn't involve unphysical concepts or appendages that may be useful but are not intrinsic to the concept of a vector. So to say that a vector points from Sun to Jupiter at this instant of time is a very clear statement, because anybody can check that. But to say that a vector has these components, then you have to ask, okay, what are the coordinate system you are using? How are you resolving it? And such questions, right? So we will do all of that, but I just want to emphasize the utility of this viewpoint. Okay, now having spoken about what a vector itself is, we can introduce the concept of a unit vector. So a unit vector is one with unit length, and by that I mean the length is equal to 1. Yeah, so a unit vector, wait a minute, I have to is a unit vector. Yeah, now so given any non-zero vector, let's call it A, yeah, we have the associated unit vector, which is obtained by normalizing it, namely dividing it by its length. So if you divide a vector by its length, you will get a vector of unit length, and we call that by the name A hat or A cap. So that is what is over here. So this is called a unit vector. Notice, of course, you cannot define a unit vector out of the zero vector, because you can't divide by 0 in a meaningful way over here. Yeah. So given any non-zero vector A, you have the associated unit vector in the same direction, and that is called A hat. Fine. And of course, conversely, given a unit vector, you can recover the vector A by multiplying the unit vector by the magnitude of A. So that is what this equation conveys. All right. Now, of course, this is a course not on vectors, but on physics. So examples of vectors are important, and these include the position vector of a particle. I mean, the position of a particle for some purposes can be regarded as a yeah. Can somebody admit Anek? Yeah. Okay. So the position of a particle, we will talk about this in more detail, but for some purposes can be thought of as a vector. I mean, in 3-dimensional space, you choose some origin, and you erect a line, a directed line segment to the particle, and you then call that the position vector of the particle. That's the position vector. Okay, now the velocity of a particle also is a vector. We will introduce this in more detail. And the acceleration of a particle can also be regarded as a vector. The force on a particle can also be regarded as a vector. Yeah. The electric field, I was talking about electric and magnetic fields. The electric field is also a vector. So at a particular point in CMI, it's actually pointing in some direction. And so also with the magnetic field, I mean, over in the atmosphere, we have magnetic fields, and they point in particular directions. They have different strengths. Yeah. So these are all examples of vectors. We will meet them in more detail and define them more carefully. Now vectors in 3-dimensional space form what is called a real vector space, denoted R3. Yeah. So this is a new concept. So vectors in 3-dimensional space form a real vector space. And what do we mean by that? We mean that addition of vectors is defined. So you can take 2 vectors and add them, get another vector in 3-dimensional Euclidean space. How is that done? Well, you take vector A, indicated here, vector B. Yeah, I mean, they both have a common origin. And the rule is to form a parallelogram with these 2 as adjacent sides. So the dotted line shows you this parallelogram. And the two sides are here, and you are supposed to form the diagonal, and the diagonal is the sum of the two vectors. Yeah, so this is the definition of what we mean by the sum of two vectors. The sum of two vectors is evidently in the plane spanned by the two vectors. In this case, it is just the plane of the paper. So that is one operation we have, the sum of two vectors. But we can also multiply a vector by a real number. So we can rescale a vector by 2 or 23 or -4, and that's going to change the length of the vector. Yeah, so for instance, if we have a vector here, we can multiply it by 2 and get a vector that is twice as long. So this is A and this is 2A, both emanating from the same origin. But of course, you're not obliged to rescale it in the same direction. You can rescale it in the opposite direction. You could even multiply it by -1/2. Yeah, and you will get a vector pointing in the opposite direction. Yeah, and it need not be multiplication by rational numbers. You can multiply it by pi if you like, or √2. You're also welcome to multiply a vector by 0. You'll get the 0 vector. Yeah, so the 0 vector is also available. Yeah, so 0 times A will give you the 0 vector, which is simply located at the origin. The 0 vector doesn't have any particular direction. You could say it points in all directions. So its direction is not defined. Its length is defined as 0, but other than that, the 0 vector does not have a direction. At least it is not defined. Yeah. Now, so a vector space is then a space of vectors. Its elements are vectors, and the space is closed under addition and multiplication by scalars. These real numbers are called scalars. Yeah, so the space of such objects is called a vector space. So vectors on the plane from a two-dimensional vector space. So vectors on the plane form a two-dimensional vector space, which I should call by some name. Do you want to suggest a name? Anybody? Or a symbol, more precisely. So you are welcome to speak up. Okay, well, anyway, so vectors on a plane form a two-dimensional vector space, which is denoted R2. Yeah, so vectors in three-dimensional space form a three-dimensional vector space denoted R3. Yeah, I am not very sure whether. Yeah, okay. All right. So, okay, so let us proceed. So please do stop me if you have a question or want to answer a question. Yeah. So now we go on to a couple of other concepts. One is that of a dot product, a scalar product. So the dot product brings in geometry. So this is the main message. The dot product brings in geometry in a quite substantial way, which will take time to understand, but we will see it in a quick way now. So if you have two vectors, call them A and B, we can form their dot product or scalar product. It's called a dot product because its symbol is a dot in between them. It's also called a scalar product because the dot product of two vectors is a real number, which we call scalars, to distinguish them from vectors. And the definition is that the dot product of two vectors is the product of the magnitudes times the cosine of the angle that separates them between them. Yeah. Yes.
So actually didn't get the point where geometry enters through the dot product. I didn't get that one.
Yeah. No, you are not expected to get it. This is going to be explained now. So, okay, one part of it has already been. So geometry, what is geometry? I mean, it has to do with lines, angles, and and other such things. So yeah, you already see things, right? I mean, you're seeing the angle between two. Previously, we just had a vector. Yeah, we just had a vector and its length and its direction. Now we've introduced, and there was no concept of an angle, right? I mean, simply not there, not defined. But now we are able to define a new geometric concept called the angle between a pair of vectors. And that angle is defined in a nice way. That angle is defined as the inverse cosine or arc cosine of what? A dot B by magnitude of A times magnitude of B. Yeah. So you see this. If you have defined this dot product, it allows you to define the angle between two vectors. And angles are geometric concepts. And that is done by using the concepts we already have at our disposal, namely the cosine function or its inverse, and the lengths of vectors A and B, which we have defined previously, as well as the dot product. Right? So this is the sense in which geometry enters. Now, I mean, this is not a light statement. Yeah, there is much more to this, but I hope I have clarified how at least angles enter through the dot product. In fact, even the length comes to the dot product. Though I was a little bit casual about it before, we can now think of the length of a vector itself as defined through the dot product. You look at this equation. If I take a vector and dot it with itself, then according to the formula given before, it is the cosine of the angle between A and A is simply the cosine of 0, which is 1, and therefore the dot product of A with A is the square of the length of A. All right. So so what we are concluding is that the length of the vector is itself related to the dot product, and so is the angle between two vectors. So again, what is geometry? Geometry is things like lengths, things like angles, yeah, the shapes of curves, the rigidity of objects. All right. Geometry has to do with the rigidity of things. I mean, if something is simply collapsible, you cannot define its length. Yeah. So that is a sense in which geometry is entering through the dot product. You will encounter this concept again and again in later studies. This is the viewpoint of Riemann, one of the great mathematicians. Great geometers. Yes. So okay. Now, as I said, the dot product is also called the scalar product, since the result is a real number, and real numbers are called scalars. So you have vectors. You multiply a vector with a number, with a real number, and you get another vector. So okay, so I will leave it as a little exercise to you to show the so-called law of cosines. So suppose you have a vector which is defined C as the sum of A and B, then it is a simple exercise to show that the square of the length of C is the sum of the squares of the lengths of A and B, plus a sort of correction term. I mean, if that term was absent, this would be basically a kind of Pythagoras theorem. But the correction to that is depends on the angle between the two vectors. The correction term is absent when the angle is 90 degrees, in which case the cosine is 0. Yeah. So I invite you to check this little formula. Now, okay. Now we will tell you about some more geometry. So the question that was asked about where is geometry is being addressed in several ways. Geometry also has to do with notions of being perpendicular or orthogonal. Yeah, so we will say that two vectors are orthogonal or perpendicular if the dot product is 0. So of course that is reasonable because we previously defined the dot product as AB cosine theta. So if theta is 90 degrees, the cosine of 90 is 0 and the dot product vanishes, right? So that's a reasonable definition.
Sir, so whenever we actually speak about vectors, we intricately refer to non-zero vectors, right?
No. Well, when I need to divide by the length of a vector, I will have to say that I am considering a non-zero vector. But otherwise, all these formulae make sense otherwise as well. So I can take the dot product of a vector with the 0 vector, right? And what is the result of that operation?
So that will be 0 itself.
Correct. The scalar product of any vector with the 0 vector is 0. Excellent. Yeah, and the length of the 0 vector can now be computed. 0.0 will be 0 squared. Yeah, I mean, it's not like we didn't know it. Yeah, but yeah, the 0 vector has 0 length. I had already mentioned that. Yeah, so most of these formulae extend also to the 0 vector. Yeah, well, it's good you asked because the next one doesn't. But before I go to the next one, I just want to point out one little thing here. We've got an interesting property of the dot product, namely that it is commutative. Yeah, it's abelian. A dot B is equal to B dot A. I mean, because AB cosine theta is the same as BA cosine theta. So we say that the dot product is commutative. So let me just write that here. And commutative means the operation commutes. A dot B is the same as B dot A. And there is another name for commutative, also known as abelian. Yeah, abelian is an adjective in honor of Abel, who was a brilliant mathematician. Yeah, so that means it doesn't matter in which order you take the dot product. We will soon meet a product which is not abelian, so not everything is commutative. Okay, now yeah. So now, of course, I didn't say, but in this figure, the two vectors are actually called collinear. Yeah, A and 2A are called collinear, point in the same direction. Yeah, I mean, even if they point in opposite directions, we sometimes say that they are collinear. So yeah, so there's a lot of terminology that is useful. Okay, now let's make use of this dot product to define another useful concept, namely the orthogonal projection. The orthogonal projection of one vector on another, or the orthogonal projection of one vector in the direction of another vector. That's a better way of saying it. So yeah, okay, so what is this? Let me first refer to the figure. So I have a vector A, yeah, could be quite long, could be short. Yeah. Now I have another vector B that's written here, drawn here. Now, when I say the projection of B on A, or more precisely the orthogonal projection of B on A, I mean this small vector. Yeah. it's also called the component of B in the direction of A. So pictorially, this is what it is. I drop a perpendicular from the tip of B to the line through the A vector. So Vishwanatha Gangadharan has entered the waiting room. Okay, great. Let's see, how many of us are here? How do I figure this out? Anyway, yeah, I hope it is substantial. Okay, so what you do is drop a perpendicular from the tip of B to the line through the A vector, and wherever it meets the A vector line, you measure the length from the origin to that point, and that length, which is now a positive real number in this case, that is called the projection of B on A. Now, this need not need not be positive. I mean, if B was pointing in the opposite direction, then I would the projection would actually be negative. I hope you can imagine that. Yeah, so they're not obliged to be at a right angle, at acute angles. So if this is A and this was B, then the projection of B on A would be obtained by extending the A vector backwards, dropping a perpendicular from there and measuring this distance and giving it a negative sign. So this is a negative projection, whereas here the projection is positive. All right. And when I said drop a perpendicular, that's why we use the name orthogonal projection. Yeah.
So when we say projection or component, we refer to a vector.
In fact, we refer to a vector as well as a direction. The vector is B, which is being projected, and we have a direction which is specified by another vector, which is whose role is being played by A. So to define this projection, we need two vectors. We need the vector A in whose direction we want to project, and we need a vector B which is being
No,
projected.
sir, I was telling that the projection itself, I mean,
Yeah.
whether the projection itself is a vector or not.
Oh, no, the projection itself is not a vector. I'm sorry. The projection is a scalar. It's a real number. Yeah.
Okay.
I mean, in this simple context, it is just a real number. It can be negative. Now, okay, I haven't actually defined it, so perhaps that is useful. I've only indicated it pictorially. So here is the formula. So you have the vector A, and from vector A, you create the unit vector in the direction of A. So that would be something like this, the unit vector, length 1. And then you take the dot product of B with the unit vector in the direction of A. Now that quantity is called the projection or the component of B in the direction of A. All right. So if you were to write it out more explicitly, it would be B dot A divided by the length of A. So clearly, I cannot project in the direction of the zero vector, yeah, because I need a unit vector, and the zero vector cannot be normalized into a unit vector. So in particular, I need A to be a non-zero vector to make sense of this concept. Yeah, does that clarify what was being asked?
Yes, sir.
Okay, great. Yeah, so that's the projection or the component of B in the direction of A. I mean, it can be in the direction opposite to A also, right? I mean, this negative projection example illustrates that. So by the way, I hope I don't speak very fast or use fancy words. If I do, please do stop me and ask me what a word means, or if you want me to repeat something. Yeah, so yeah, I am aware that since I have typed these things out, I may tend to go a bit fast. My tradition is to write on a board, in which case you see equations and symbols and words being developed. Right now, I'm not quite doing that. So please do stop me if I'm rushing. But I will try to make these notes available to you so that you can go over them. But don't count on that. I mean, I'm not obliged to do so. Be present and learn. It's very efficient to learn in the class. It takes longer to learn later on and so on. Okay, so let me see where we are. Okay, we could of course do the opposite, that is to project A on B. Now these are not the same thing. Yeah, but I will let you imagine what that is. I mean, you basically have to reverse the roles of A and B to define the projection of A on B. Yeah. So okay, so just a remark that the projection or component of B in the direction of A, does it depend on the length of A? Please tell me.
No, sir.
Correct. Yeah.
Yeah, it
Is,
should not.
is independent
Okay.
of the direction of A. Yeah. So I hope. Sorry. is
Length of A.
Sorry, you're quite right. It's independent of the length of A. It only depends on the direction of A. Yeah. Okay, so that's a good point to bear in mind. So that's why in English we say it's the projection of B in the direction of A, or the component of B in the direction of A, not along A. Just to clarify. Okay, let us then move further. Now the scalar product I have introduced is quite useful in physics. Many concepts use it. We have already talked about its geometric utility, namely in defining angles or lengths of vectors, concepts of orthogonality or collinearity. All of these are related to the dot product, but so are many physical concepts. Just to illustrate one, we have the concept of the work done by a force acting on a particle. So suppose you have a particle here. My particle begins here. A force is applied to it. Now this force may be somebody pushing it, or maybe it's charged and there's some electric field. Yeah, or there's some spring to which it's connected. But let's make it simple. Let us suppose there's a constant force that acts on the particle that pushes it in this direction along a vector, a displacement vector. So this is a displacement vector. Yeah, I called S. Yeah, little s. I could call it small s. So and it is the force doesn't change. Let us keep things simple. The force is constant. It pushes the particle from a point A to a point B, you might say. Then let's say a point whose vector location is A and a point whose vector location is B. Then the displacement S is given by what formula?
B minus A.
Correct. So this is my origin. This is vector B and this is vector A. Yeah, so S is B minus A. Yeah. See, sometimes I find it convenient to draw an arrow above the symbol. Sometimes I simply draw this. You will find what is convenient for you. Yeah, I will answer the question, the text box from Bijay and Rai. But one moment. So I've not yet said what the work is. So you have a force, in this case, a constant force that displaces a particle along a straight line along the vector S, displacement vector S. Then the work done by the force is defined as the dot product F dot S. All right. I mean, this only works for a constant force, but I think that's a good place to begin. Yeah, so this is one place in physics where the dot product enters. Now, the question that is asked is, what is more generic, force or work or energy in the sense what arises in nature and what is a mathematical definition. Now, okay, there are several questions here. So far, we've not talked about energy, so I will come to that. Okay, so we will speak of energy. All these concepts, work, force, energy, they're all important physical concepts. They all arise in nature. Or rather, okay, I don't know in what depth to answer this question. They are all mathematical definitions. See, we observe nature. Nature doesn't tell me I'm doing work. Yeah, nature doesn't tell me that, anything. We observe nature and we draw conclusions. We verify, we check those conclusions. Other people check them. So this process is called the mathematical modeling of natural phenomena. Yeah, so when we mathematically model physical phenomena, natural phenomena, we introduce various concepts that are helpful for that. Now, you can ask the question whether these concepts are purely mathematical definitions or have physical use or are physical. Now, I think they're all, of course, mathematical definitions. Yeah, sometimes they take time to make them into proper mathematical definitions. They may be somewhat vaguely defined. But I think the question can be answered in a practical way. A concept is physically relevant if it can be measured in the first place. Yeah, I mean, can you measure the work done by some device? Then of course, then it is something physical. Can you observe it? Yeah, can you measure it? I think that is a good way to test whether a concept you have defined mathematically is physically useful. Okay, maybe you can't measure it. Yeah, there are many things you can't measure directly. But if it is useful to find some other physical concept that can be measured, yeah, that enters in some intermediate stage of a calculation, then again it is helpful. Yeah, I mean, it has utility. It may not be directly physically measurable, but it may have value in the computation of some other physical quantity. So such things are also valuable. We may not call them directly physical quantities, but they are useful. So I hope that clarifies to some extent. I think the word generic has been perhaps not intended in the question. What is more generic? So the word generic, I doubt that is what Vijayan really meant. Yeah, the word generic has a different meaning. At least I am not able to understand the sense in which it has been used here.
I think like in physics, like we try to model the laws which inform some mathematical statements. So like which can be made more axiomatic. We can work all the calculations in physics using just work or using just restricting force. For there is always equivalences comes in between them. So more generic in that sense.
Oh, okay. Okay, the word generic. Okay, maybe you mean what is more fundamental or something like that. Yeah, well, what is more basic? What is more elementary? Perhaps that's what you mean. Well, as you notice, to define the work, it's not enough just to know the force. You need to know also how the particle was displaced from where to where. Yeah, so it's not as though you can compute the work only knowing the force. Yes, the force in some sense is more basic because it is an ingredient that goes into the computation of the work, at least as I have defined it here. I mean, displacement again is more basic because the particle is displaced and then you compute the work that's done. Yeah, so in that sense, the displacement is a more elementary concept than work. And the force is a more basic concept than the work done by the force. I mean, even the sentence itself conveys that. Yeah, but physics works in strange ways. There are times when a concept that is defined in terms of something else, it is sometimes possible to recover in the opposite direction. Yeah, I don't know, who knows? Maybe one day we will be able to recover the force from the knowledge of the work it has done, right? So we have to be open to such possibilities. We have to be open to such possibilities. I cannot emphasize that with more. I cannot emphasize that more. Yeah, physics is not an axiomatic subject, right? the mathematical modeling of physical phenomena is an attempt to bring axioms into physics. Now, this may or may not succeed. That is, of course, our holy grail. But your axioms may or may not be what nature wants. So we learn through experience and trying things out. You may set up a system of axioms where some things are more fundamental and others are more derived. But later on, it may turn out that that whole system can be reversed, and there are another set of axioms from which you can deduce these conclusions. So we have to be a little bit open-minded about such things. An axiomatic formulation of a physical system is in some ways a later stage of development. The study of the physical system, the examination of how it behaves, how it reacts, what are its features, these are what we begin with. We get experience that way. We try to deduce some axioms. The axioms don't come first. The examples comes first. The examples, the phenomena, the observations, they come first. From those observations, we deduce axioms. This is the way it goes. And by the way, this is true in mathematics as well. The definitions are the last thing to be given in a theory. So it took a very long time to define what a manifold is. There were 1,000 examples of manifolds before a definition came. So we have to be very careful about how we set things up.
So given a set of axioms, let's say that you take a guess that describes nature, how do you make the relevant predictions to see that they really hold true or not?
You use logic. You use logic and some mathematics and some other such mumbo jumbo and all your intuition and your luck and your friends' help and your teachers' suggestions. No, I'm serious. This is how it works. But the thing is that it doesn't work that way. You don't just set up a system of axioms and try to check. Sometimes it works, but it really is a back and forth process. You make observations, you see what's important, and then you deduce that, oh, okay, maybe it's helpful to define a vector called the force. Or maybe it's useful to define a concept called the location, and then the small change in location is also relevant. So it goes that way. It's a back and forth process. In some exceptional cases, people have at least it appears that people have set up a system of axioms and try to deduce consequences. And that is, of course, a process that is through analysis and algebra and geometry and logic. And then you set these things up, you deduce consequences, like, okay, you say, you make some postulates, and then you deduce the consequences, and then you check those consequences against what is observed in nature, in other experiments, in other phenomena. If it agrees, then you receive some confidence in those axioms. I mean, it's very important to know that no axiom can be proved. No axiom, no physical theory can be proved. We have to be very, very clear about this. In mathematics, you can prove a theorem. There is no such concept in physics. You cannot prove a theory. You can only falsify a theory. You can have your proposal, your favorite ideas, your favorite postulates, your favorite logic, and the favorite conclusions. This is good as long as it describes nature. And then we will be happy with it. We will keep it. But it can not be proved, because you can only check it against one experiment, one more experiment, your grandfather's experiment and your granddaughter's experiment. But that's all. You only check a few experiments. However, if even one of those experiments shows a disagreement with your axioms or with the conclusions drawn from your axioms, then that theory is wrong or has been falsified. All right. So in physics, we can only falsify statements. We can only falsify theories. We cannot prove theories. I mean, we can check a calculation, but that is simply a mathematical process. Okay, so does that address your question at least a little bit?
Yeah, Professor. Yeah, sir. Yeah, it does.
Okay, all right. I can hear a smile, though I can't see it. Fine. Okay. Yeah.
Sir, I have a question. Like, I wanted to ask what exactly energy and momentum is, because in both of these forms, we somehow have a velocity kind of a thing. So something is moving. Now, when
Yeah.
I think of motion,
Wait,
it is
wait.
basically
Whoever is speaking, is that Aryan
Sir,
Kusre?
Sir Punja.
Sorry, what was Ripunjay? Yeah, okay. I would request you, I mean, I'll let you finish your question, but I would just suggest that we wait a little bit because I've not defined velocity, I've not defined energy yet. So we will come to all these things, and perhaps your questions will be better addressed at that stage.
Okay, sir.
Yeah, but okay, but I really do welcome questions. So just go ahead and finish what you're asking.
So my question is like, in all the physics that we have described and in all the physics that we do, we never account for the fact that like when the motion is happening, an object is basically leaving a point in space and then it is occupying another point in space. We just don't seem to be concerned about how this exactly is happening. We just say that this happens and this is represented by a velocity function and all those things.
Yeah.
So I wanted to ask, like,
Okay.
isn't it basically throwing the real physics under the rug that we just don't consider how all of this is happening?
Okay, I mean,
Just
it's
because we can
very,
make predictions, we just don't consider it.
yeah. No, I'm okay. Okay, it will take me time to absorb your question, but see, I think one has to at some stage take a pragmatic viewpoint. If it is helpful to talk about the velocity of a particle, if it helps you to make predictions, if it helps you to understand eclipses, if it helps you to dispel some misconceptions, or predict when something is going to happen, then it's a useful concept. So if it helps to consider the motion of a particle from one place to another as being described by a curve, excellent, please use the curve. And if it helps to call its instantaneous change in location per unit time as something called a velocity vector, I think it's very useful. So I think it's helpful to take that viewpoint. Um, um, that is what physics is. We observe phenomena and find useful mathematical constructions to describe those phenomena and predict new phenomena. That is our business. We are not sweeping the physics under the rug. We are actually discovering physics this way. Yeah, but no, I mean, maybe your question will get further refined over time, and you're welcome to ask it again. But does my statement have any relevance to what you're asking?
Yes, sir, it tells us that, like, it tells me that why we are doing it, but I still have that thing that why are we not addressing that phenomena, because even that is happening.
Which phenomenon? We
So
want to
like,
observe the motion of Jupiter. Yeah. So what are you going to do? You keep looking up. If you don't have a telescope, you just use your naked eye. You make a chart in your book. You mark some location of some stars which are far away that don't appear to move. Yeah, and then over the whole night, when you don't sleep, you mark the position of Jupiter as you observe relative to these so-called fixed stars. And then it, like in school, you find a bunch of dots, you join those dots, yeah, because you don't observe it at every second, and you join those dots and you say that's the trajectory of Jupiter. Now then you form the tangent vector to this curve and say that's the velocity of Jupiter. Yeah, now I think we made progress here. We've understood how Jupiter moves relative to the fixed stars. And this is the kind of thing that Kepler and not Kepler, I mean Tycho Brahe and others did. That is what we mean by physics. We are making progress that way. Yeah, I have another question from Bijayan. Like in study of differential equation, we usually like to consider the invariants or terms are conserved. Yeah, we will come to concepts of conserved quantities. Definitely, conserved quantities will and invariants will play an important role. So please hold on. Any other question at this stage? Okay. Okay, now the last topic that I can discuss in this lecture is that of a vector or cross product. So this is another type of product which many of you may have encountered. So just like the scalar or dot product had two names, the vector or cross product also has two names. The vector product of two vectors A and B is again a vector. So that's why it's called the vector product. So it's a vector, so we must say what its magnitude and direction are. Its magnitude is defined as the product of the magnitudes of A and B times the sine of the angle between them. All right. So, so okay, the cross product also brings in geometry because the sine of the angle enters, but it's bringing things in a slightly different way. So here theta is the angle between the vectors. Now I haven't yet told you the direction of the cross product, so let me draw a picture to explain that. The direction of the cross product is defined by a very human process of using your hands. So let's see. I have a vector A, I have a vector B. Okay. And I want to compute or define A cross B. That is the cross product. Now it's defined as a vector which is perpendicular to both A and B. That's part of the definition. So A cross B is perpendicular to both A and B and points in the plane perpendicular to A and B. I mean, that is the same thing. So it points in the plane perpendicular to A and B, and points in orthogonally to this plane, the plane spanned by A and B. And you want to know which way? Well, you do the following procedure. You so suppose this is vector A. I invite you to look at my photo, my video. So you have vector A here and vector B here. Yeah, you have these two vectors, and I want to compute A cross B. A cross B. B is the white pen. A is the dark colored pen. Now the cross product is defined as pointing in the direction in which the thumb points when the fingers of the right hand curl from the first vector to the second. All right. So the fingers curl from the first vector to the second, and then the thumb points towards my nose. All right. So that's the direction of the cross product. A cross B points towards my nose. Yeah. So in this example that I've drawn here, A cross B is going to point out of the plane of the paper. Yeah. So A cross B points out of the board or out of this paper. So this symbol will designate pointing out of plane. Plane of the paper. On the other hand, B cross A, I will start with my fingers pointing towards B and then go towards A, and my thumb will point in the direction of the cross product. So in this case, B cross A points into the plane. And that is usually denoted by a little circle with a cross inside it. So this is some simple-minded notation, but it is widely used in elementary physics. So given any two vectors, you have the so-called right hand thumb rule. All right. So this is a very concrete process. It tells you concretely how to compute the cross product. It tells you which way it points, tells you its direction, it tells you its magnitude as well. Some people prefer the so-called screw rule. We can talk about that another time, but I want you to get used to one rule, and I think the right hand thumb rule is as good as any. So if the fingers of the right hand curl from A to B, then the cross product points in the direction of the thumb. Now, interestingly, let us finish with this observation that the cross product is not commutative. All right, because we just observed that A cross B is out of the plane, whereas B cross A is into the plane. Yeah, and therefore they can't be equal unless they're both zero, of course. Yeah, and therefore A cross B in general is not equal to B cross A. So the cross product is not commutative. So it's non-abelian. It's a non-abelian product. So you see that physics forces you to invent geometry, forces you to invent algebra, forces you to invent analysis. So anyway, it is nice to learn physics. That is my message. I think I am now out of time. It's 1:05. We shall then continue on Thursday, unless there are questions about what we have discussed. Any questions right now?
Hello.
Yes.
So what is the difference between the scalar 0 and the 0 vector? I mean, the 0 vector doesn't have a specified direction. So
True,
how
true.
is it different?
Yeah. Oh, no. You're very good question. The scalar 0 is a real number. It's just one real number. The vector 0 is not just a single real number. We will later on talk about representing a vector through components. We will do that. And when you do that, you will find that the 0 vector actually has 3 components, all of which are 0. Yeah. So in that very concrete way, 0 vector and the scalar 0, the real number 0, are simply not the same. They live in different spaces, is another way to say it. The 0 number, the real number 0, lies along the real line. Yeah, I mean, it's the point at the origin of the real line. Whereas the 0 vector lies at the origin of 3-dimensional Euclidean space, right? These are completely different things. So that's another way to convey that they're very different. The 0 vector is not the same as the 0 number. 0 vector is not a real number. Yeah. Okay. Does that address your question at least partly?
Yes, sir. Yes, sir. Thank you, sir.
Yeah, sure. Any other questions? Okay. Any comments about the setup? Any difficulty with the audio, video, and viewing the notes and so on? Okay, fine. Anyway, so thank you all for joining us. No, sir, everything was fine. No difficulty for me. No difficulty. Okay, great. Yeah. So anyway, I'm very happy to make your acquaintance in this very impersonal manner where I cannot see anybody. But in fact, I'm still wondering how many of you are here. Where is that number displayed? Or can someone tell me?
So there are 64 students other than you
and the 2 TAs. Okay, 64 students. Great. Thank you so much for joining. So enjoy your lunch and good luck with your time at CMI. I welcome you all here and have a good afternoon. I will send additional information about problems and so on that are to be done. We will communicate primarily through email and Moodle, and things will be posted on the website as well. Okay, so all the best. So please take care of yourselves and stay safe. If I can have just the 2 TAs remain, I would like the rest of you to leave the meeting.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
You're welcome.